Here's lesson 2 of the trig geometry unit. In this lesson, we'll use special triangles and reference angles to find the value of trig ratios for angles that are bigger than 90 degrees. Up until now, you've used sine, cos, and tan to find angles or side lengths in triangles. But if you follow along, I'll extend your understanding of what these functions can be used for, and we'll start to work with angles bigger than what you would normally find inside of a triangle. So the first thing we have to learn is how you're going to start to think about angles. We're always going to imagine that we have a Cartesian grid, and we have something called an initial arm, which you see in blue on the positive x-axis. And the terminal arm is an arm that rotates around the origin away from the initial arm in a counterclockwise direction if we have a positive angle, or in a clockwise direction to represent a negative angle. And that terminal arm and the initial arm between them is our angle theta. The next thing we need to look at is the difference between what's called a principal angle and a reference angle. So if I look at this diagram on the right, notice that we have a terminal arm that is rotated some angle theta counterclockwise away from the initial arm. That angle between the initial arm and the terminal arm in the counterclockwise direction is called our principal angle. And now every principal angle has what's called a related acute angle, which is sometimes referred to as a reference angle. And what that reference angle is, it's the angle between the terminal arm and the closest x-axis. So that angle, usually we use beta to represent that reference angle, and it's the angle between the terminal arm and the closest x-axis. So that's our reference angle right in there. Those reference angles are going to help you to determine the exact trig ratios when the angles given are obtuse angles. So let's practice finding reference angles before we actually see how they're going to be used. So for each of these principal angles that are given, let's find the related acute angle, the reference angle. On each of these grids, I'm going to start by labeling the positive x-axis with 0 degrees, and then in a counterclockwise direction, I'm going to label every 90-degree interval. Notice that 0 degrees and 360 degrees are in the exact same spot. We call those angles coterminal angles. For a principal angle of 250 degrees, I know that means that from the initial arm, from the positive x-axis, I go counterclockwise 250 degrees around the origin. That would land about right there. So this angle from the positive x to the terminal arm is 250 degrees. That's our angle theta. I'll represent that angle by labeling at the tip of the terminal arm 250 degrees. The reference angle for 250 degrees is the angle between that terminal arm and the closest x-axis. So what's the angle between 180 and 250? We can just find the difference in those two angles. And if I do that, I would find out that the reference angle, which I'll call beta, is equal to 70 degrees. That 70 degrees is this angle inside here, the angle between the terminal arm and the closest x-axis. Now let's look at 120 degrees. From the initial arm, rotate counterclockwise 120 around the origin, and that would bring me to about right here. So that 120 represents this angle right here. And then the reference angle is the angle between the 120 degree principal angle and the closest x-axis, which is 180 degrees. The difference between 180 and 120 is 60. So the reference angle, beta, is 60. Let's try another two. Let's do 300 degrees. From the initial arm, I'm going to rotate 300 around the origin in a counterclockwise direction. That would bring me to about right here. The reference angle is the angle between that 300 degree terminal arm and the closest x-axis, which is 360 degrees. The difference between 360 and 300 is 60. So my reference angle, beta, is 60 degrees. And lastly, 225 degrees. Rotating 225 counterclockwise from the initial arm brings me to about right here. The angle between 225 and the closest x-axis, between 225 and 180, their difference is 45. So the reference angle is 45 degrees. Now that you know how to find reference angles, let's start to figure out what we're going to use these for. When we have an angle theta that is rotating counterclockwise around the origin, we're going to imagine that it's tracing a circle. And that terminal arm is going to intersect the circle at some point xy. If from that point, I think of a right triangle connecting down to the x-axis, and using the radius of the circle as the hypotenuse of the triangle, I can start to imagine the trig ratios, sine, cos, and tan, of the angle theta as being ratios of the sides that are in this triangle. Now, if this point of intersection with the circle is some point xy, to get to that point, I would have to go x units that way, which is why that side's called x, and then y units that way, which is why this side's called y. And this side is called r because it's clearly the radius of the circle. Now, if I express sine, cos, and tan of that angle in terms of these sides of this triangle, I can use x, y, and r. Remember, sine, cos, and tan, we usually express in terms of opposite, adjacent, and hypotenuse. So from this reference angle theta, I know that y is the opposite side, x is the adjacent side, and the radius, that's the hypotenuse. So my sine ratio from the reference angle, sine is opposite over hypotenuse. So in this case, it's y divided by r. Cosine of the reference angle is adjacent over hypotenuse. So that's x over r. And tan of the reference angle is opposite over adjacent, which is y over x. Starting to think about the sine, cos, and tan ratios in terms of the x and y coordinate of where you intersect the circle is going to help you understand what we're going to learn next, which is something called the cast rule. The cast rule is a rule that's going to help you remember what trig ratios are positive in which quadrant. So first of all, the quadrants are numbered based on the order that you would rotate through them. Remember, we rotate counterclockwise around the origin. So this is the first quadrant we rotate through, so that's quadrant 1. Here's the second quadrant, third quadrant, and fourth quadrant. In quadrant number 1, all the ratios are positive. But in quadrant number 2, only the sine ratio is positive. Well, why is the sine ratio positive? Well, if we look at how we define the sine ratio is equal to the y coordinate divided by the radius of the circle. Now, radius of the circle will always define as positive, but y coordinates are not always positive. Y coordinates are only positive above the x-axis, so here and here. That's why in those two quadrants, the sine ratio is positive. But in quadrant 3 and 4, y coordinates are negative. That's why in those two quadrants, you see that sine is not positive. In quadrant 3, only tan is positive. In quadrant 4, only cosine is positive. Which means in those two quadrants, sine is negative. And then also, how do we define cosine? Remember, cosine is equal to the x-coordinate divided by the radius. Well, where are x-coordinates positive? That's to the right of the y-axis, so here and here. And notice those are the two quadrants where cosine is positive. Where are x-coordinates negative? In these two quadrants. That's why you see cosine is negative in those two quadrants. Right? In this quadrant, sine is positive, but cosine and tan are negative. In this quadrant, tan is positive, but cos and sine are negative, and so on. So let's summarize that in this chart to the left. In quadrant 1, all ratios are positive because both x and y are positive in that quadrant. In quadrant 2, only sine is positive, since in that quadrant x is negative, but y is positive. In quadrant 3, only tan is positive. And in quadrant number 4, only cosine is positive, since in that quadrant, x is positive, but y is negative. And instead of having to think about the x and y coordinates every time we do a question, you could just write out the cast rule, which tells you which ratio is positive in which quadrant. Let's move on to where we're going to find the exact value of a bunch of trig ratios for angles bigger than 90 degrees. To do this question, you're going to have to remember your special triangles. Anytime we want the exact value of a trig ratio, you need your special triangles. I've redrawn the special triangles off to the side here. We'll need to reference those as we do these questions. The first question just asks for sine 45. We don't actually need to draw this Cartesian grid for this question because sine of 45, sine is opposite over hypotenuse, so sine of 45, I can just do 1 over root 2, and there's my answer. But let me draw this just so we practice how we're going to do these questions as they get more difficult. I start by drawing the terminal arm, which rotates 45 degrees counterclockwise from the positive x-axis. The reference angle is the angle between the principal angle and the closest x. So the angle between 45 and 0 is, of course, 45 degrees. If we're in quadrant number 1, the principal angle and reference angle are going to be equal to each other. I'm also going to label my cast rule, and then circle the fact that we are in the all quadrant, which means all trig ratios are positive in this quadrant. So I can say that sine of 45 degrees is equal to, referencing SOHCAHTOA, sine is opposite over hypotenuse from 45, that's 1 over root 2. This answer can be rationalized. Multiplying top and bottom of this by root 2 would give root 2 over root 4, which is just root 2 over 2. So there's the final answer for sine of 45 degrees, and it's an exact form. Let's try a more difficult one, sine of 210 degrees. If I rotate 210 degrees, that means rotate around the origin in a counterclockwise direction, 210. That would land you right here. The reference angle is the angle between that terminal arm and the closest x-axis, so the angle between 210 and 180. The difference between those two is 30 degrees. Now here's where the question gets a little bit tricky. If I want sine of 210 degrees, I can, instead of finding sine of the principal angle 210, I could instead find sine of the reference angle 30. But remember cast rule. Based on cast rule, notice we're in the tan quadrant, a quadrant where only tan is positive. So sine of 210 cannot be positive, which means I can use the reference angle 30 as long as I remember to state that it's going to be a negative ratio. So sine of 210 is actually equal to the negative of sine 30 degrees. And sine of 30 degrees, we can look at our special triangle. From 30 degrees, sine is opposite over hypotenuse, which is 1 over 2. So sine of 210 would be equal to negative 1 over 2. So there's our exact answer for sine of 210. And let me take a second and explain to you why this works. Let me zoom in a bit. The most important thing for you to understand is this statement right here and why it works. Well, let me draw what a principal angle of 30 degrees looks like. It would be in quadrant 1, and its reference angle would be 30. If I draw a circle centered at the origin, we know that a sine ratio for any angle is equal to the y-coordinate divided by the radius. Well, the radius in both of these cases is the same, but how do the y-coordinates of these 2 points relate to each other? Because the reference angles are the same, I know that they are the same absolute distance away from the x-axis. So I know these side lengths are the same, but the y-coordinates are obviously not the same. In quadrant 1, the y-coordinate is positive. In quadrant 3, the y-coordinate is negative, but they have the same absolute value. So because these y-coordinates have the same absolute value, but obviously this one's negative and that one's positive, that's why we're able to state that sine of 210 equals the negative of sine 30. Let's try another question. Let's do cosine of 240 degrees. If I have a principal angle of 240 degrees, that's going to land right about here. The reference angle is between the terminal arm and the closest x-axis, so the angle between 240 and 180 is 60 degrees. Based on the cast rule, I know that we're in a quadrant where only tan is positive, which means cosine is going to be negative. So if I want cosine of 240, I can do cosine of the reference angle, 60 degrees, but I'm going to have to make that ratio negative because in this quadrant, only tan is positive, so cosine has to be negative. And then if I want cosine of 60, I can go to my special triangle. Cosine of 60, well, cosine is adjacent over hypotenuse, so I would do 1 over 2. So cosine of 240 is equal to negative 1 over 2. And let's try one more. Let's do tan of 315 degrees. Rotating 315 degrees is going to land me right about here. The reference angle is the angle between 315 and 360. The difference between 360 and 315 is 45 degrees. So the reference angle, beta, is 45 degrees. Based on the cast rule, I know that in this quadrant, only cosine is positive, which means my tan ratio is going to be negative. So if I want tan of 315 degrees, I can instead do tan of the reference angle, 45 degrees, but I'm going to have to make this ratio negative because in this quadrant, tan is negative. And if I want tan of 45, I can find my 45 degree reference angle. Tan is opposite over adjacent, so tan of 45 is 1 over 1, which is 1. So my final statement will say tan of 315 equals negative 1 over 1, so negative 1. So there are my exact final answers for those questions. Let's see what other types of questions we can now solve. Example 3 says each point lies on the terminal arm of angle theta in standard position. Determine each of the primary trig ratios for angle theta. Part A says 5, negative 12 is on the terminal arm for angle theta. So let me just roughly plot where the point 5, negative 12 would be. And it says that point is on a terminal arm that is rotated angle theta from the initial arm. I'm going to connect this back to the x-axis to turn this into a right triangle, and then I'm going to use what I know about trigonometry and the cast rule to be able to write all three trig ratios, sine, cos, and tan, for angle theta. Remember, angle theta is this angle right here. Now, there is a reference angle in here, but since I don't know what angle theta is equal to, I can't calculate the reference angle, but I will call it beta. And I do that because based on the cast rule, I know that I can use the reference angle beta to get my trig ratios as long as I consult if I have to make the ratio negative or not. In this quadrant, only cosine is positive. So cosine of theta is equal to cosine of the reference angle. I can leave it as a positive answer. Sine of theta would be equal to negative sine of beta, and tan of theta is going to be equal to negative tan of the reference angle beta. Notice I'm making the sine and tan ratios negative when I switch the principal angle to the reference angle. But I got to leave the cosine ratio positive when I switch the principal to the reference because in this quadrant, cos is positive. And now to get these ratios, I need the side lengths of this triangle. To get to this point 5, negative 12, I would have to go 5 that way and then 12 that way. So I know the side lengths of that triangle are 5 and 12. And then based on Pythagorean theorem, you could calculate the hypotenuse to be 13. Using those side lengths and your understanding of SOHCAHTOA, we can write all three ratios. Sine from beta would be opposite over hypotenuse, which is 12 over 13. So sine of theta is equal to the negative of that. So it's negative 12 over 13. Cosine of beta, cosine's adjacent over hypotenuse, so it's 5 over 13. Cos of theta is equal to cos of beta, so that equals 5 over 13. And tan of beta would be equal to opposite over adjacent, so 12 over 5. Tan of theta equals the negative of tan of beta, so it's equal to negative 12 over 5. So there are my three ratios. Let's try another question. Part B says point negative 8,3 is on the terminal arm. I'll draw a terminal arm that has that point on it, and then connect it down to the x-axis to make my right triangle, and label my cast rule. Remember, this is angle theta. That's what we want the ratios for, but I can use the reference angle beta as long as I remember that I can leave the sine ratio positive, but I'll have to make the other two negative. To get to this point, negative 8,3, I would go 8 this way and then 3 that way. So I can label those two side lengths, 8 and 3. And then based on Pythagorean theorem, I could solve for this side length to be the square root of 73. If I want sine of theta, I can do sine of beta, which is opposite over hypotenuse, which would be 3 over root 73. If I want cosine of theta, I can do the negative cos of beta, and cos of beta would be adjacent over hypotenuse, which is 8 over root 73. So cos theta equals negative 8 over root 73. And tan of theta, I can do the negative tan of beta. Remember, tan is opposite over adjacent, which would be 3 over 8. So tan of theta equals negative 3 over 8. Now, these two answers could be rationalized by multiplying top and bottom by root 73, which would give me the following answers. So here are all my final answers for the exact values of all three primary trig ratios for angle theta. Let's move on to something called a unit circle, which is going to be useful for figuring out the exact value for ratios that land exactly on the x or y axis of the Cartesian grid. So for angles of 0 or 360, 90, 180, or 270. Now, the unit circle is specifically a circle with a radius of 1 unit. That's why it's called a unit circle. If we have a circle with a radius of 1, notice in this triangle that I've inscribed inside the circle that we're rotating around, I've labeled the radius as 1. If we know the xy coordinate of where we intersect that unit circle, it actually makes calculating the sine, cos, and tan ratios very easy. Let me label this reference angle theta in here. And then based on SOHCAHTOA, we can write an expression for each of the three primary trig ratios for angle theta. Sine is opposite over hypotenuse, so from theta, that would be y divided by 1, which is of course just equal to the y coordinate. Cosine is adjacent over hypotenuse, so cos of theta would be x over 1, which is just equal to x. And tan is opposite over adjacent, so tan of theta would be y divided by x. So if we know the coordinates of where we intersect the unit circle, the y-coordinate gives us the sine ratio for the angle, and the x-coordinate gives us the cosine ratio for the angle. And there are 4 points that we would easily know the coordinates of. And because this circle has a radius of 1, moving 1 unit in any of these directions gives me the coordinates of these points that are on the circle. So let's go ahead and evaluate exact values for sine of 270 and cos of 360. I could communicate what the answer is going to be by drawing a unit circle on both of those grids, and then drawing a terminal arm that rotates whatever the principal angle is, so 270 and 360. I'll start with the 270 degree terminal arm. If I rotate 270 degrees, the terminal arm is going to intersect the unit circle at this point right here. And the coordinates of that point, because the radius of the unit circle is 1, I know I've gone 1 unit below the x-axis, so this point will be the point 0, negative 1. I want sine of 270 degrees. Well, if we look back here, the sine ratio of any angle is equal to the y-coordinate of where you intersect the unit circle. And I know the y-coordinate of where I intersect the unit circle is -1. So I can say sine of 270 is equal to -1. And that's it, that question's done. If I want cosine of 360 degrees, well, I'll draw a terminal arm that is rotated 360 degrees. It would rotate all the way back to where it started at the initial arm. Because this circle is a unit circle, I know its radius is 1, so 1 unit in that direction brings me to this point right here, which is the point 1, 0. And if we remember, if we want a cosine ratio, the cosine ratio of any angle is equal to the x-coordinate of where you intersect the unit circle. So the x-coordinate of where we intersect the unit circle is 1. So cosine of 360 is equal to 1. We have a couple more quick things to learn before this lesson is over. Negative and coterminal angles. Let's start with coterminal angles. Coterminal angles are just angles that have the same terminal arm. And because they have the same terminal arm, all their ratios are going to be equal to each other. So for example, if I rotate 30 degrees, or if I do 360 more degrees from there, that would be 390. Or another 360, that would be 750. And then another 360 would be 1110. All of those angles, which I have represented in each of these diagrams, all land you in the exact same spot. They all have the same terminal arms. We say they're all coterminal angles. Anytime you add 360 to any angle, you get an angle that is coterminal with the original angle. We could also subtract 360. That would also give you a coterminal angle. And that brings up the idea of negative angles. If positive angles are measured counterclockwise from the initial arm, negative angles are measured clockwise from the initial arm. And there's a note here that explains if you have a negative angle, what you could do is just add 360 to it, and that would give you a positive angle, which is coterminal with your negative angle, right? If I rotated 150 degrees in the positive direction, that would land me in the exact same spot as going 210 degrees in the negative direction. So negative 210 and 150 are coterminal with each other. Example 5 just asks you to find 3 coterminal angles with 60 degrees. I'll call them theta 1, theta 2, and theta 3. If they're going to be coterminal with 60 degrees, I can just add 360 degrees to each of them. So theta 1, I can just take my 60 and add 360. And that gives me 420 degrees. Theta 2, I can just add 360 to 420 degrees. Or another way to think about that is I can add 360 2 times to my initial angle. That would give me 780 degrees. And to find angle 3, how about we mix it up? How about we take our initial angle, 60 degrees, and subtract 360? That'll give me a negative coterminal angle. It'll give me negative 300 degrees. So all of these angles, negative 300, 780, 420, and 60, they're all coterminal. They would all have the exact same terminal arm. So let's put all this together and find the exact value of a couple trig ratios that have a negative angle. We'll once again need your special triangles, so let me redraw them down at the bottom here. And now if I want sine of negative 45, I'll start by drawing the principal angle of negative 45. That would mean go 45 degrees in the clockwise direction, which will land me down here in quadrant number 4. Because I went 45 in that direction, I know that 45 degrees is my reference angle. Also, don't forget cast rule. Based on cast rule, in this quadrant, only cos is positive, which means my sine ratio is going to be negative. And I can switch it to finding the sine ratio of the reference angle. So it would be equal to negative sine of 45 degrees. And sine of 45 degrees, remember, find my 45 degree angle. Sine is opposite over hypotenuse, so it would be 1 over root 2. So sine of negative 45 equals negative 1 over root 2, which we should rationalize, multiply top and bottom by root 2, which gives negative root 2 over 2. There's the answer to that question. Let's do part B a little bit differently. Let me start by changing this negative angle to a positive coterminal angle. I can do that just by adding 360 degrees to that angle. Negative 60 plus 360 is 300 degrees. So I can do cos of 300 instead of cos of negative 60 because negative 60 and 300 are coterminal. And let me actually demonstrate that to you. It wouldn't matter whether you rotated 60 clockwise or 300 counterclockwise, you would land in the exact same spot. You would have the same terminal arm. So I'll label at the tip of it negative 60 or 300. Those are coterminal angles. And both of those angles have a reference angle, right? The angle between that terminal arm and the closest x-axis. That angle, the difference between 360 and 300, is 60 degrees. And then based on cast rule, I know that in this quadrant, cosine is positive. So if I want cos of 300, I can instead do cosine of the reference angle, and I can actually leave the ratio positive because in this quadrant, cos is positive. And cosine of 60, well, I know cosine is adjacent over hypotenuse. So from the 60 degree angle, do adjacent over hypotenuse, and I get 1 over 2. So cosine of negative 60 is equal to 1 over 2. There you go. If you followed along with that lesson, this has a lot of brand new stuff for how we're dealing with trigonometry. So make sure you understand everything fully in this lesson before continuing with the unit.